check the audio.
Yeah. YOLO. Okay. How this works. And I realize it's kind of useless. Okay. Okay, yeah. Cool. Alright. Yeah, so I can get rid of this. I can undo stuff like this. No, it doesn't work. Yeah, okay. Just Control Z. Okay. Yeah, I think we're ready. So yeah, welcome to Math2601 Revision Seminar Part 2. Yeah, today we'll be covering like the last three topics. So I think the last one's determinants. So here we'll be covering eigenvalues and eigenvectors, followed by Jordan form, and then matrix exponentials, which is powers of matrices. Okay. So eigenvalues, a bunch of eigen stuff. So just recall from 1b, essentially eigenvector is if you apply a matrix transformation, instead it could be shifted, if there's some random vector, when it's mapped under a linear map, it could change its direction or do some random transformation like that. But specifically for an eigenvector, it's a vector specific such if you map it under this linear map, then it will maintain its direction, or maybe just scale up some constant factor essentially. So the fact that it's scaled by is called the eigenvalue. The vector which is remains its direction is called the eigenvector. And essentially we can have a set of all these eigenvalues, which is called the spectrum. So I believe the set of all the eigenvectors is called the eigenspace. So a bunch of definitions. So I believe Brennan covered this yesterday as well, but invariance is when for a linear transformation, if you map your vector under your transformation, then it still remains a subspace under that whatever space you're under working with. So for just some random subspace U, if you apply linear transformation to it, it's still subspace of U as well. So that's T invariance. Okay, so here we just have a bunch of random properties here for eigenvectors. So eigenvalues are, so that one's kind of obvious. Eigenspace, so it's specifically again the vector space of all the vectors such that if you map onto the linear map, it's some scalar version of itself, or more formally, it's specifically the kernel of your linear transformation minus your lambda times by I, because it's kind of the definition what we do in 1b is simply determine this to be 0, or essentially just asking what vectors will make that basically 0, which is essentially the kernel. So next thing is invariance. So V is also an eigenvector, so is transformation of T of V. If you have different eigenvectors under different eigenvalues, they'll also be linearly independent. Then eigenspaces. Again, if you have different eigenvalues, then this eigenspaces again will be disjoint. Essentially, there's no vector that will kind of be in both, maybe a different eigen. Oh, sorry. There's no eigenvectors gonna be in both here and here. Technically the only one's gonna be the 0 vector. But yeah, that's kind of what it means destroying vector, destroying eigenspaces. Finally, the big one, I guess. Matrix is diagonalizable if and only if you can kind of represent a basically sandwich a diagonal matrix. So diagonal matrix is the one like all the diagonals are basically just like your eigenvalues, and you sandwich it between like a matrix like invertible matrix P and P inverse. Where they find like the matrix P will be all your eigenvectors that form your matrix A, and that's assuming it's like diagonal. So there's enough eigenvectors essentially. Yep. So multiplicities. So I guess like when we did like 1B again, kind of represent the characteristic polynomial. So it might be like, okay, it's really a bit annoying. Not like that. So you might like get like some random, I guess, characteristic polynomial, something like this or whatever. So that's an example. So essentially, like this like degree here basically represents like the number of eigenvalues you should get essentially. So we're gonna call it like the algebraic multiplicity. So literally just the degree of your characteristic equation. But then here now we're kind of like having this new notion of like geometric multiplicity, because sometimes when you have only like one eigenvalue but has like a lot of multiplicities, it doesn't like automatically mean that you have like one eigenvector. You could get two eigenvectors associated with a single eigenvalue, but sometimes you might just get like a single eigenvector associated with like one eigenvalue but has like a lot of like multiplicities. So that's why we introduced this idea of like geometric multiplicity, where the number of eigenvectors associated with your eigenvalue is called the geometric multiplicity. So like more formally again, like that's kind of like representing using this dimension of the kernel. So like again, it's like the nullity. So how many like vectors like below like, or basically just how many eigenvectors it is associated with that eigenvalue. So we just call it like the GM, I guess. So because like one of these like I guess like theorems is that like no way you can have like more eigenvectors than like your like characteristic equation. Comes a bit silly, but it's definitely like bounded. So it's like definitely like less than algebraic multiplicity, because what it says like you could get up to the algebraic multiplicity itself, but you may not get exactly like the like in this example here, you may not get like the eigenvectors. You might only get like one or something. It has to definitely at least be one. We can definitely say like one is like the geometric multiplicity of any like eigen like value essentially at least has to be one. We can definitely say that. Yeah. So kind of like what I'm saying before. So matrix is generalizable if not only for like every eigenvalue. The geometrical multiplicity is actually equal to the algebraic multiplicity. So then basically just saying like, oh yeah, for every single eigenvalue, we have like enough eigenvectors to like basically make up our matrix P. So that's kind of like what this like probably here is saying. So some of all the and yeah, so essentially like if they are equal, then they have like n linearly independent eigenvectors. Like even if you have like one eigenvector that's kind of off, then that's definitely not enough to like form your matrix P for like the invertible to like sandwich between your diagonal matrix. Okay, so just a bunch of random examples here. Find all the eigenvalues of like each of these matrices. So, so just like the thing from 1B, minus the lambdas of these, except the determinant to be 0. So I can like just product of like this. So minus 2, so it's like plus 2. So that equals 0. So m squared 2. Oh, I'm missing something. Okay, so lambda squared 5 lambda plus 6 is 0. Factors. So it's 2. Okay, so here we just see like the eigenvalues like 2 and 3. And then how do we find the corresponding eigenvectors? So kind of just like chuck in like each of these like eigenvalues into like respective like here, I guess. So what we have is minus 1, 2, minus 1, 2. And then once you like subbed in your eigenvalues, you basically just want to force the kernel to be 0. So like this is definitely got multiple like double in here, so that's gone. So you have like this, and I guess like an eigenvector here is just like something that makes it 0. We can say like 1, oh, I say 2, sorry, 2, and like 1. So like -1 times 2 is 2, and then plus 2 times 1 is 2, so that will equal to 0. So that is an eigenvector. Times equals 2. And then -3, we can do like -2, 2, -1, 1. And then again, like just the multiple of the bottom. And then here, what's something that can make it 0? Well, we just say like 1, 1. So like -2 plus 2 is 0. So we have like 1, 1. So the eigenvalue again associated with that is like 3. So those are your algebraic, oh no, these are your eigenvectors, and basically these are the eigenpairs, actually. So eigenpairs is basically just like the vector along with its eigenvalue. They show also like algebraic and geometric multiplicity. So like, if we go back up here, kind of just like basically just like for algebraic at least, you just like notice like what the power of here is. Like each is like obviously like power to 1, so all of them power to 1. So that's the algebraic multiplicities, and then geometric multiplicities is just like how many vectors could you find associated with that eigenvalue. So we all got like 1 here anyway. So yeah, both of these are all equal to 1. Yeah. Okay, and then I don't have that much space. Okay, maybe like do it here or something. 2. It's 3. Yeah. Okay. So, tell me of this one. It's like I'm just getting like minus lambda here already. Okay. So I guess like a trick here is the determinant is just gonna be like if you do like that thing for like 1a or something, it's like this thing times like the determinant of this. So it's like 3 minus lambda, 3 minus lambda, minus 1, and then you like kind of like minus like these kind of thing. Like it's like -0 times all these and like +0 times all these. But of course, like these are like 0. It's kind of easy because like we'll go to 0 anyway. So like we don't need to worry about that. So this will be the 2. 2 minus lambda means like lambda squared minus 6 lambda. It's just expanding out. So 9 minus 1 is 8. It's just like that. I mean, this we can like flip around because we're saying to equal to 0 anyway. Doesn't matter. This here we can like factorize into like lambda minus 2 and like lambda minus 4. Yeah. So then like the roots here, it would just be like 2. So, with a 2 and 4. So we kind of like notice here is like lambda equals 2. It's like a double root. Like we've got like 2 of these here. Lambda 4, that's like a single root, so that's fine. Again, we have to like just find the eigenvalues associated with this. So I might have to go rid of this space. Let's find 2. So 0, 0, 0, 0, 1, 1, 1, 1. Yeah. Obviously, the third was just kind of like a copy. So get that out. Okay, I have to like do this kind of thing. So like x3 is like lambda. In x1, that like truthfully has to be equal to 0. Oh, it's 0. Wait. No, we can say like x. Wait. Look at x2. So x2. X2 plus x3, so just lambda. That's equal to 0 again. So we just find that x2 is equal to minus lambda. We got one leading column, so we have to have 2 free variables, I believe. So just set like x1 to like some other random variable, so like mu. So we have is like mu minus lambda. So we have like split it as like 1, 0, 0, and then like 0 minus 1, 1. So that's essentially 2 eigenvectors there associated with just lambda is equal to 2. So we see here like the geometrical multiplicity here is 2, which is like kind of nice because it lines up with the algebraic multiplicity. And then you do like a similar thing again for like 4. So that one, -2, 0, 0, -1, -1. Once again, it's kind of like a copy of the second one. So -2, 0, 0, -1. Okay, so we've got 2 leading columns, so like we should get one vector in the kernel here. So I think it's x3 is lambda, x2 is also lambda. Oh yeah, x1 has to equal to 0. So because like it doesn't matter like what these are to go away, and then like what times -2 is like 0 in the answer is 0. So in the end we just have like 0 lambda lambda, or just like 0 1 1. So that should be associated eigenvector with lambda equals to 4. Yeah, let me check if I'm right. 0 1 1. Yeah, okay, good. It's right. Oh, okay. Well, I mean, like, this is the negative of that. So, like, you can change, like, make it negative, the same thing, essentially. Like, did it ask for eigenspace? He didn't say eigenspace, but, like, you can kind of, like, determine, like, essentially, like, what the eigenspace is like, it's just a space of, like, all the, it's, like, the span of, like, all your eigenvectors. So, if I said, like, the eigenvalue of, like, E2, just asking for the span of, like, all, like, these vectors here. Like that, and then that. And it's like similar for E4. So I kind of like, it's already written here anyway. So yeah. So because the algebraic multiplicities is equal to their geometrical multiplicities for each respective eigenvalue, then that means like there's enough eigenvectors, so then like therefore the matrix is diagonalizable essentially. Okay, so each of the years given characterizing the okay. Okay, I'm gonna kind of cheat here because like I think I'm gonna say later we can like kind of use properties of the matrix to like determine specific parts of like the eigenvalue. So I'm gonna use the fact that like the trace of your matrix is equal to the sum of your eigenvalues. So this trace here, that's like 3. So like 2 minus 3 plus something is equal to 3. So then equals 4. That has to be eigenvalue. Yeah, like we all have like one, like all the eigenvalues are definitely unique here. So we can kind of conclude like the algebraic multiplicity is equal to 1, and so is the geometric multiplicity. Like it can't be 0. Okay, meanwhile for this, D. Yeah, let's like multiply this out. So like 1 0 1. That's equal to 1 plus 2, so it's 3. So I'm gonna like cheat here again. It's like I know this is definitely an eigenvector because like that's the question set up. So like this like the first entry multiply what is equal to 3, so it's just gonna be 3. So I can like kind of guarantee like this eigenvalue here is equal to 3. I'm gonna do like a similar thing here. So just multiply that by 142 and like 2 negative 1 2. It's kind of like scuffed like notation, but like to work with it. It's like 2 minus 4 plus 4 equal to 2. So basically, like the first entry remains unchanged. So if you multiply your eigenvector is equal to itself, the eigenvalue is basically 1. So eigenvalue is 1. So basically with this, then once again, we kind of like use the fact that the trace of it is going to equal to the sum of the eigenvalues. So I already have 3 and 1. Trace is 8. So I can kind of deduce the other eigenvalues definitely going to be 4. So lambda is equal to 4 for other eigenvalue. Okay. Yep. Oh yeah, like obviously like for the geometric and algebraic, once again the AM and the GM is like all 1 anyway. Yeah. Okay, so kind of like a bit more. There's like conditions for diagonalizability. So T is diagonalizable. There's a basis. So it's like the your P matrix that sandwiches the diagonal matrix. There have to be eigenvectors. These are the direct sum, so like of like all your eigenspaces. So like think about it as like the span of like all your eigenvectors essentially. And then yeah, like again, like the sum of the geometric multiplicities is equal to not the algebraic multiplicity, but the dimension of V. So again, it's like once again, you're trying to like fit the span of like V, because if you like one vector off, then it's not gonna be enough essentially. All right. Okay. VB vector space to be linear map. So kind of like working like a different basis here. So like you're transforming each of these essentially. So yeah, essentially it's like, is there a basis so that this is essentially diagonal? So okay. So we can like try like I guess find the matrix T, because like I think like in 1B there's like that theorem, like the matrix representation theorem. That's what I remember. You can basically represent a linear map of like a matrix. So when doing this, initially I thought it was like the coefficients of like these ones, and you kind of like just copy like row for row. But actually can't do that. It's like kind of like you have to flip it or something. So essentially like the coefficients are like here essentially. So this is like 0 to 0, but then that becomes like your second row essentially. Oh no, that second row becomes like your second column. So it's like this. And it's like the same thing. It's like 0, 1, 1. Again, that becomes like a column instead. So it's like 0, 1, 1. Because like if you did like essentially like multiply this out. So like if we did multiply by V1. So I know like V1 isn't like a standard basis, but like let's just pretend that it is indeed like 1, 0, 0. So like let's just say it's this. Then essentially like what you're gonna get is like when I multiply that by here, you're gonna get the first column. So that's equal to like 2, 1, 1, which kind of like by going by logic of like this is like a 1, 0, 0, 0, 1, 0, and then like V3 is like 0, 0, 1. Like you see like it does like match up. So it's kind of like the proof like this matrix here like does work. So when you have this matrix here, at that point now you just need to like ask like is this thing like basically diagonalizable? Or like so like we probably just like find the eigenvalues of this. So once again it's like that massive process of 2 minus lambda, 2 minus lambda, 1 minus lambda. In this case though, I think the determinant is like much easier because like it's gonna be like this times by like the determinant of this one. But the determinant of this one's like, oh, this times like 0, so like we don't really care. Like 2 minus lambda and then 1 minus lambda. And then like once again, like all these, like it doesn't really matter because like, when you do like the I guess like determinant form of the thingy, like the 0 times like whatever determinant like these columns, like it's gonna be 0 anyway. So like again, that's not like a big deal. So like just from this, we can kind of see like the eigenvalues are like lambda and 1. 1 and 2, that is. So we want to check if like when lambda is 1, like that's not an issue. Maybe the issue is when we have like lambda equal to 2, because the geometric multiplicity may or may not be in our vectors essentially. So we just gotta check when we submit lambda equal to 2, like do we have enough like vectors in the kernel essentially of like 1 minus 2. So I like going here. 3 minus 2 is like 0, 0, 0, 1, 0, 1, 1, 0, minus 1. Okay, so we have like this. Okay, and then like what can we do from here? X3. Okay, now we're gonna like plus the columns, plus the rows. Sorry, 0, 0, 0, 1, 0, 1, 2, 0, 0. So essentially, x. Okay, let's just say like x3 is lambda. X2. I believe that's like a free variable. So we get mu, but then x1, just because of this, it has to equal to 0. So, ooh. No, that's a bit of a problem. Okay, I'm just gonna change like look. So, okay, it's like it's literally just this, but okay, so you like shift, you make that on the top, and then okay, it's like minus that off. Okay, so like basically like they just conclude like the kernel is equal to 101,002. Then from here, then you have two leading columns. So the rank of this is basically 2. So the kernel is like 1. So okay, better like say dim. So if we only want to prove like it is diagonalizable, we don't even need to find the eigenvector. We just need like find the dimension of it. That's all we care about because that is the geometric multiplicity. So the geometric multiplicity is like 1, but then we're saying that the algebraic multiplicity of this one is equal to 2. So that's a bit of a problem because at that point it's not diagonals. You don't have enough eigenvectors. So to answer this question, no. Not enough eigenvectors. Okay, that's essentially that. All right. Okay, so like I know we're like coming like 2501, but yeah, there's like sometimes like a bit of gaps here. So apparently like spectral theory that is like in 2601, but in 2501 is like not. But like they learn apparently to my knowledge they learn like some special case of it or something. So like I guess like it is kind of like nice to know, but it's like if you don't understand like entirely, like it's like not necessary. Just pray it doesn't appear in the exam or something. So a linear transformation, the definition is like it's normal if and only if the map is like essentially it commutes with the adjoint where like you basically just swap the order. So like normally this isn't true for like matrices, but if it just so happens that like that is true for a matrix with its adjoint, then it's basically called normal. Oh no, this is basically maps. But magic it's like the same thing. So like just like again like swap the order. Yeah. Okay. So essentially like idea like spectral theory is like you get a bunch of facts like this if your linear map is normal. So if it's normal, then like your linear map that is, it's like kind of the norm of your matrix applied to like the transformation. It's the same as like the same thing, but like with its adjoint essentially. Then if the matrix is normal, then it's kind of like the setup with that like eigenvalues. That thing will also be normal. And yeah, it's not even like an eigenvalue. Like it can be like any number within your field basically. And also for the eigenspace, comparing with its adjoint, it's like going to be the same eigenspace, but it's have like a different eigenvalue, which is going to be like the conjugate because I don't know. I guess that's like kind of like related to like the adjoint because like when you calculate the adjoint, you're taking the transpose, but you're also like taking the again like the conjugate. So I guess like that's kind of like where it comes from. But again, like you can't do like the algebraic proof to like kind of figure that out. So again, if like 2 is normal, then if you have like distinct eigenvalues, then the eigenspaces corresponding to those distinct eigenvalues, they're going to be orthogonal to each other essentially as well. Yeah. Okay, so I might have to like go back to these a lot because the questions I'm going to say afterwards, like I'm going to basically refer back to this. So if A is like a normal matrix, then the eigenvectors of it is orthogonal. And there's also like a unitary matrix. So I think like from what I remember, it's like unitary is like oh I know it's like the adjoint is equal to is like its inverse essentially. So that's what unitary is. Especially if you have a symmetric matrix. So a symmetric is the one where like it's like the same basically, but for Hermitian, you take the transpose, but then you have to like take the conjugate. But if you have a symmetric matrix, I believe this is like the same thing. But the only additional thing is that you have all the eigenvalues are real. Yeah, so it's like the same thing as above. And then if you have a unitary matrix instead, then like the first one I just said is gonna be different. It's actually the eigenvalues. They all lie on like the unit circle. It's like the like basically this thing. It's like that is equal to 1. So counting that, whatever eigenvalue it is. What's I? Oh wait, it's all real. Yeah. All right. So it's like some final like 2020. So. Okay, good. So that's our matrix here. So assuming here like P is orthogonal, so I'm just got like confused about this. So pretty certain that P it's also normal because like essentially like okay like symmetric I forgot like the thing away like essentially like when it's under like the real and like the complex like fields, it's like there's like different names essentially. So like it's like basically like depending on like what field you're working on, because like it's all real. Then essentially like normal is wait, so like adjoint is the same thing as its essentially like the transpose. Um so here like it's like the same as the normal. Is what I'm pretty certain about. So either way, like again, show like the kernel of that is equal to like, the span of these like vectors here. So yeah, okay, like a bit of math here now. So we have to minus off a single I. So be careful like how we do on the diagonal because we don't want like minus off like one like that. Because like we have like this one factor of like 109. So it's like essentially like 509 minus 1. So it's like 509 minus 909. So it's like you're essentially like minusing off 9 off of these diagonals if we would like basically like keep that essentially. So that would be like -4. These are fine. Yeah, I'm just gonna minus off 9 right away. So like -1, -9, -4. Okay, no, these are the same. Okay, so what can we do from here is like a bunch of kernel stuff. So what I'm noticing is like this here is just like the negative. So I'm just gonna like divide that by 2. So like oh yeah, like at that point, like if I'm only concerned with the kernel, then I really don't care about like the 109. So I'm just gonna leave that alone. -2, 1, -3, 2. It's like the bottom's like 0, 0, 0. What's some other stuff? Yeah, okay, like this is kind of close, but like that's not exactly a multiple of like the third row, but it's like the double negative of like the first row. So like again, like that goes away. The third row, yeah, it's not really like it's like a multiple of the first one, but I would like divide by 3 just to make it easy, I guess. So 2 -1 -3 -2. So essentially, we just have to like get the kernel of that. Yeah, it's honestly like kind of quick. To like do like this x4 is like lambda, and then wait, I could just I can maybe like plus them. Like -2, 1, -3, 2, 0, 0, 0, 0, and plus them. So like 0, 0, -6 is 0. Yeah. So like what can I deduce about like this third row? I can like kind of like say this whatever that value is for x3, like it has to be 0 because like everything else is 0. So like I can definitely say x3 is 0. But then maybe let's say like x4 is like still lambda. Yeah, we got like the rank is 2 here, so it's like 2 leading columns, and then means that we have like 2 free variables here. So maybe something like that. Nah, maybe like let's say like x1 is mu. Okay, so we just need to find like x2. So x2 is equal to 2 mu plus 3, but that's nothing, minus 2 lambda. So writing it out, I think it's like mu, 2 mu plus 2 lambda, 0 lambda. Okay, so like kind of like splitting this up, we get like okay, let me do mu first. 1, 2, 0, 0. And then the other one's in lambda is like 0 minus 2, 0, 1. Okay. So those are my like that's the span of my kernel here. And you might be feeling like, oh, like why is this like not the same as like these and like where's the similarity? It's really just like the linear combinations with it essentially. So like it's like if I like plus this along with this, I should get like this vector here. And then like how to get this one? Oh yeah, it's like this vector minus this. So yeah, like it does work out anyway. Yeah. Okay, next this might be interesting. Like why is the spectrum of P equal to this? So how do it's 1? So like when we're calculating in general, like when we do like if it's no. Okay, so like okay, I'm just gonna say lambda instead. Okay, if we ever asked like find the kernel of this, then whatever vectors you find in that kernel, that should be your eigenvectors associated with the eigenvalue of like lambda. In this case, we said that lambda is equal to 1, so like 1i. And we found two vectors there. They're like li. So essentially like the double root, like the eigenvalue of 1 is kind of like a double root here. So we already have like two eigenvalues here. It's pretty good. But then where do you find the inverse? We're gonna again use the fact that the sum of the eigenvalues should be just equal to the trace, just by looking at this. So what is it equal to? So 5 plus 8 plus nothing 5 over 9. So 18. So that's just like 2. So we already have like these two here are 2. So then the sum of our eigenvalues of the other two, that is, should be 0. Now, because this is, and this is the part where I have to like kind of go back. There's like one of these here. So okay, so it's definitely not that. Okay, so this one here is unitary. Okay, let me like this. Okay, like dot product, this kind of thing. 10 plus 16 minus 18 minus 8. Yeah, okay, 26. Okay, yeah. So this thing here is definitely unitary here as well. So like the last is like obvious, but like this is the one we're going to use here. All the eigenvalues lie on the unit circle. So how does that help our case? Because let's say that, okay, because the other thing is the eigenvalues, I believe they should also come in conjugate pairs. I don't know which one it comes from. Yeah, I'm not sure like which one of those it's from, but okay, maybe it's like kind of like implied here, like lie in the unit circle. Okay, because the real part of like both of these, that should equal to 0, because if it wasn't, let's say it's like a half plus I. Okay, well it doesn't really like lie in the unit circle. Okay, so like that. If you're like that plus or minus the conjugate pair, well then the real part when you like sum them, it's not going to equal to 0, and if it's not equal to 0, then it's not going to equal to the trace along with like the sum of these two. So the only way that you can have like your like the real part, like will basically satisfy it, is when the real part of it is actually equal to 0. So then, okay, then like what about the imaginary part? The only way for that is essentially like I negative I, because they still lie on the unit circle. Like if it's like some multiple of it, then it's not on the unit circle. So that's essentially why. Okay. That's essentially like why it has to be like I and negative I, because like they lie on the unit circle, and like the root part of it has to go to 0. So like what I said here, yeah. So the eigenvalues have to be on that essentially by a spectral theorem. Oh, okay. So if it's somehow that, oh yeah, okay, because like if you did get like somehow 1 again, then the geometric multiplicity would be like it would be like 3 basically. But like we already calculated from before, like that first part, it was already 2. So like we don't need like any more the copies of 1 essentially. So yeah, that's why I get like these two additional eigenvalues here. Okay, so I don't remember. I think this is 1b. I don't think it was 1a. A rotation matrix can be represented like this form. So like a bunch of like alphas here essentially. Now the eigenvalue of this is e to the I alpha. So it's kind of like representing like, oh, if you times this matrix by some eigenvector, it's going to rotate. By how much? By I believe alpha here. So like where alpha is like the angle that you're going to rotate by. Okay, so yeah, a bunch of like beefy matrices here, but every orthogonal 3×3 matrix is going to be like unitarily similar to like either one of these matrices. So you notice like it's like the same like rotation matrix, but it's like a plus or minus 1 on the top in the corner. So if if the like the top left corner is like actually wait. Yeah, if the top left corner is like 1, it's just gonna be a it's gonna be just a rotation by like whatever alpha you're gonna rotate by here. If it's -1, then you're actually gonna have to do a reflection first, and then followed by a rotation. So okay, it's gonna be bit hard to draw, but I'm trying to say here, there's like a YZ plane, YZ plane, and then this is like this is the x-axis that is. So if this is like your eigenvector, if it was the first one, then it would just like rotate by like if this is like that might be like alpha. However, though, if it's the second one though, it will make a reflection through the plane to the normal of like your eigenvector. I wasn't meant to say that, but like it's meant to be through that plane there, and then you do your rotation. So hopefully my drawing kind of sucks here, but like that's kind of what it means for the second. Like do reflection and then you do your rotation here. Alright, and also the other thing is determinant here is like 1, and determinant here is like -1. So you know, like if you calculate your determinant, you can like and it's orthogonal. You can like deduce like, oh yeah, like what's it gonna do? Like rotate, or like you're also gonna like reflect as well. Alright. So okay, so it's kinda like similar to like since like when I said about the determinants, then you kinda again like include like it's similar to like that first case and like similar for like the negative case, essentially. You can also determine the like trace of it by not other way around. So like you can determine the like the angle of it by using the trace, because again, if you look at like the matrices, then like some of all these is like depending on like whichever case you're talking about, like plus or minus 1 plus like 2 of your cosine alphas, that's going to be your trace. You can then like deduce what the alpha is going to equal to just by like rearranging. Okay, so give a geometric description of this. So, so just like do the determinant. Okay, it's a bit of a pain. So, determinant A. So, remember that thing from like, I guess what Rashid would have said yesterday is like, if you have a fact inside your determinant, if you take it outside, it wouldn't just be like, oh, 1 over 9. It would be like 1 over 9 to the power of like whatever matrix power you have. So, it would be like 1 over 9 to the power of 3. So, like this. The inside stuff I can't really skip, so like I have to like do it. It's like -4 and then -4 plus 32, -4 minus 32 minus 4 plus 7, 64 minus 1. Okay. You're like bit of a pain. I didn't even get the right value. -4. Oh wait, it's meant to be a friggin' minus. Okay. Alright, so the massive inside, okay, like that is like 729, but the inside thing though is 729. Okay, so like that works out nicely. Term is 1. So again, because I mean, we're just assuming this thing is orthogonal. Like, just do like the pairwise like dot products, like and then you're also just checking like each one of these, like the length's like 1. So definitely always orthogonal. So the thing is determinant 1. So that means like, oh, okay, it must be like unitarily similar to like that first case we said. So it's just a rotation only. So, but by how much that is, it's just going to be like -4 plus 1 minus 4. That's equal to 1 plus 2 cos alpha. So again, like -4 plus 1. Okay, so that means like -709. So cos alpha. -709. Okay, so it's like -809. Okay. So like obviously you like cos inverse it, but like whatever angle that is, that's how much you rotate the your eigenvector by essentially. So okay, I was meant to like check this off photo, but like it's kind of obvious. Yeah, so like it was kind of like that spoiler kind of setup thing. Whereas like you're doing like some rotation about what though? You rotate about an axis of like some vector, but like specifically what vector is that? It's specifically the eigenvector that's associated with that eigenvalue, like in this case maybe like one or like -1, whatever it is. And yeah, it's like the same case with like the negative eigenvalue, eigenvector. Okay. So great. I haven't summed it right. Why is this? Nah, it's a bit bogus. Nah, it's meant to be a surely. Yeah, the fours are the negatives, not this one. So yeah, we'll talk about my part, so that's on me. Yeah. In this case, yeah, like we're not like you can just do the calculation, but the eigenvector associated with like 232. So you're gonna like rotate your eigenvector. Okay, yeah. Yeah, so essentially you just like rotate your vector of rotation around by like suppose like this angle here, around the axis of like 222, which is your eigenvector here. Okay, I really don't want to do this, but freaking okay, SVDs now. So so like singular value is it's gonna be like the square of like whatever eigenvalue you have. So yeah, freaking massive like process here, but it's equal to like u and then like sigma of like the adjoint of like your V matrix. Um, yeah, like I think like the sigma is kind of obvious, but like when we like point X, like I keep, like making this mistake. The sigma like it wouldn't like let's say your eigenvalues are like 5, 3, and like 1. Like it wouldn't just be like √5. Oh no, it's meant to be like say like 0. Maybe say it's a double. Like it wouldn't just be like 5, 3, and like 0, 0. Like these like basically won't matter. You'll always like basically when that happens, you basically get rid of it. Get rid of those rows. Basically get rid of like the non-zero rows, like non-zero eigen like get rid of the zero eigenvalue rows. So you'll always have you'll always the number of columns will at least always be greater or like equal to like the number of rows essentially. So it'll be like that. Because like here, like it can be an m by n, so like not necessarily like a square. The other two are square essentially. So yeah, that's like kind of the one thing. Oh, yeah, it's one thing about SVDs. Okay, so yeah, just like to reiterate the you have like so many freaking algorithms in this course, but for SVD, find the eigenvalues is kind of obvious, but put them in descending order, and yeah, like the other annoying things like you have to make sure it's unit length, and you have to do like this weird ass process where you have to do like ui is equal to like 1 over square root lambda I, and then times like the original matrix that you're trying to SVD followed by the like the normalized eigenvector. You'll never get a case where the you're gonna find like the square root of the eigenvalue. Like it's never gonna be 0 because you're gonna have enough eigenvectors to like not count this case essentially. Okay, and then yeah, okay, like on the more like I guess like orthonormal base vectors using Gram-Schmidt process. And yeah, you form those like vectors like u and v. But then this one here again is kind of simple, just like square root like the eigenvalues. That's kind of 3. Okay. Okay, for speed up step 1, so A star A and A star they have the same like non-zero eigenvalues essentially. So rank A is Q, then okay, yeah. So like it's kind of just saying like oh yeah, like A star A must have like Q non-zero eigenvalues, but like all the other eigenvalues have to essentially equal to 0. So that's your limit here. And then this is useful when the usual case is like n by n. Yeah. So if it's m by n, it's like you have like m by 2, then n would represent your columns. Yeah. So like this is saying we have more columns than your rows. Then you should basically do this essentially. So I'm going to use it right here right away. So for this matrix, find the eigenvalues of a star. So yeah, once again, I just more bashing here. So no complex stuff here. This is fine. 11. Three. Let me calculate for this. -3 plus 3 plus 1. Okay, 1. Okay. And then we're using the fact that this is symmetric, so that's fine. Because that's the property of A star A or vice versa. Oh wait, I need to find the eigenvalues. Okay. So you can do something like lambda minus 11 squared minus 1 is equal to 0. So lambda is equal to 11 plus or minus 11 plus or minus 1, so 10 or 12. We don't need to find the eigenvectors, so it's fine. We need later. But why the eigenvalues are also eigenvalues of A star A as well? I mean, we can just use the lemma I just said, up here. They all have the same non-zero eigenvalues. I think I might be able to prove this. Wait, so A star A, that's equal to some random eigenvalue like this. What you can do here, you can probably maybe A star A this both sides. So A star lambda V, but then this thing here, just let that be some random vector. So just call that U. So then we just have A star A is equal to U, that is equal to this is the constant, so just bring it here. But then again, that thing's U, it's lambda U. So yeah, it's it's definitely not gonna be the same eigenvector, but it still retains the same eigenvalue. Just by this little quick proof here. So yeah, it's kind of proof I guess that lemma above as well. Y must be the same. And all the other all the eigenvalues have to be 0 because I believe this is this is a 2 by 2. Then A star A, that's a 3 by 3. Any other eigenvalues of that has to equal to 0 essentially. Because that's basically what the lemma says here. Yeah, so these eigenvalues is again the same because that proof there, and has all the others have to be 0 essentially. Yeah. Okay, find all the eigenvectors of A star A. This one's not that bad. Okay, let's say 10. Yeah, this is 11, 11, 1, 1. So 1, 1, 1, 1. So eigenvalues, eigenvectors 1, negative 1. Lambda equals 12. Negative 1, 1, negative 1, 1. Okay, so eigenvector this again is 1, 1. So yeah, those are the eigenvectors. Then now I have to freaking do this SVD. So the sigma one is kind of easy. So why not just write out the square roots of all our eigenvalues? So we already said it was square root 12 and then root 10. Now what's Okay, so I believe. Okay, I'm just gonna cheat here. Pretty soon it has 2 rows. Oh, what the hell is this sigma? Okay, yeah. So I would say it would be 0, but then again because it has a non okay, no. It would be 0, but then again, just take out all the rows involving 0 eigenvalues. Just get rid of that. Would have been a 3 over 3, but then remember that row is just now a 2 by 3. So that's your sigma here. Of course, when we find our what's that formula here? Yeah. Okay. So when we find our eigenvectors here, of course we have to like normalize it. So this like better be better. I better say like this kind of things like that. It's like similar for the bottom. So 1 over 2, 1, 1. Okay, so now I have to like apply each of these like eigenvectors to like that random process, I think. So it's like the one on like the sigma AV. Yeah, just like that. Pretty soon. Yeah. Okay. 1 on root 12. 3, negative 1, 1, negative 1. Okay, B. Okay, 1, 1. So I have to like bring out 1 on root 2. It's like 1 on root 24 of. No, I messed up. That's a 2 by 3, but then this is a 2 by 1. So dimensions don't line up. Okay, I'm gonna cheat again. Because like freaking SVD is so cooked. Oh crap, wait. I did the wrong one. Damn it. Okay. And if I ask for freaking misread this. It's meant to be eigenvectors of the other one. So like get the other one. Oh god. Do it up here. 3, negative 1, 1, 1. 3, 1, 1, negative 1, 3, 1. Okay. Okay, no, at this point I can't be seeps. Like, was it like, okay, 10, 10, 10, 10, 2. Above 4, 2. Okay, and then we just like gonna like use the symmetric property of this. Just like that. Okay. But like the eigenvalues are still the same, so like you can still do like the minus 10 and all that. So 0, 0, 0, 0, 0, 4, 2, 4, minus 8. Clearly the top is the second one is like a multiple of the bottom. Okay, I'm just gonna say like 1. 0, 0, 0, 1, 2, negative 4. Okay. Kind of once again, like the x3 that has to go to 0. And then what can like make this 0? So we can like say 2, negative 1. So that is my associated eigenvector. Lambda 10's okay, whatever. You know what I mean. Minus 12. So minus 2, minus 2, minus 10, 4, 2, 4, 0, 2. Okay, what's it this time? From the top, we have minus A. Okay, good. So once again, like just a multiple of like the first one. I'm going to divide by 4 actually. So 1, negative 2, 0, 0, 0, 1, 2, 5. Okay. Wait, why is this? Okay, yeah, no, that's fine. Right, okay, now I'm like paranoid my answers are wrong. Okay, that's right. And then did I do that wrong? Wait. 2 minus 12, 10. Oh, okay, whatever. I'm just gonna cheat there. The eigenvector of that is like 1 to 1. Okay. And you also got like the when lambda is equal to 0. So like the lambda is equal to 0 is like not a, like a it's not a useless case. Like we still need to calculate to like put it in like our V matrix. So like yeah, at this point I'm just gonna cheat. Okay, so like the other one is like negative. Okay, negative 1, negative 2, 5. Why is this not okay? M equals 0, 1, negative 2, 5. Okay. So then we have to like freaking yeah, these are the ones like we normalize. Okay, so my vector's like all over the place. I have to do it here. I'm just gonna look down here. That's the point. 1, 2, 1, and then normalize, so like 1/6. It's like limit is 12. Limit is 10. That one was 2, 1. So I believe it's 1/5. I already forgot it. Wait. Finally, limit is equal to 0. Where is it? Okay, -1, -2, 5. Okay, so 25 plus 5. That's 1/30. Okay, so these will form my V's essentially. So like I'll write that at the end. So actually no, it's right now. Okay, so it'll be like 1/6, 2/6, 1/6. Next one, -5, 1/5, 0, -1/30, -2/30, 5/30. So that'll be my that'll be my matrix V. So now we just have to like do this again. Not again, but like I have to find our U vectors essentially. So U is equal to like the massive process again, like 1/12, and then A. So -3. No, 3. Yes, use this. 3, 1, and then times by the first one, so it's like 1/6, 1 to 1 is equal to √72, so like 6√2. 2 by, oh yeah. Okay. 3 plus 2, 6. Then 6, 7, 6. Okay, so it's kind of clean. So it's like 1/2, 1, 1. And we have to do the same for the unknown. So really, okay, wait. Let's do it. So 1/10, 3, 1, 1, -3, 1. It's like 1/5, -2, 1, 0. Let's go to 5√2. -5. 5. Okay, so we get like 1√2, -1, 1. So then our vector U is then equal to I would just say again like 1/2, 1/2, and here it's like -1/2, 1/2. So we have our matrix U with our sigma like up there, and then we have our vector V's, which is this. So hopefully that's right. Yeah. Okay. Now just importantly, like sometimes like the question might ask like, "Oh, find a single value decomposition," like because like what might trip people up is like this like this adjoint thing. So like if you actually like actually. Yeah, no, just like basically like, your vector V is your matrix V is that, but then like when you're actually like, doing the calculation, you have to like take the adjoint that. So like you just be careful about that. Yeah. Okay, fine. Took way too long. Jordan form. So wait, check the streams I've worked. Ooh. Okay. Looks like it's good. Okay, so freaking Jordan blocks. So basically behind the Jordan block is like you have your it's basically represents like a diagonal matrix, except you have a bunch of ones randomly like above the diagonal, so it's like the super diagonal. Yeah. So like essentially if we have J of like K lambda, like K is just like the size of your matrix, and like lambda is like the eigenvalue just put in for like each of the diagonals. Like, okay, so like these are a bunch of random examples. So like, I just have like J of like 3 of pi. Like that's equal to pi, but then like above each of those is like a 1, like this. So random example there. Yes, same. Okay, so what's kind of important about like joint form is that you have like these powers here. So it's like a 1 by 1. I don't know what that's doing. But if you like do the pattern here, you find it's like NC1, but it's like the lambda also appears there, but it's like it's the power of n minus 1. And like similar for like if you have like that 3 by 3 case. So like you get like these ones here, but like that's NC2 on there as well. So I don't know, it's kind of like a I'm kind of envisioning this as like a slanted like Pascal's triangle sort of thing. I don't know if that's like where it's actually meant to come from, but like that's my intuition behind it. Yeah. Like I don't think an exam like you can get like a 4 by 4 case, something like that. Yeah. So like, these are like the powers like drawn forms like the first one's obvious, but then you're essentially like doing this for like every like sort of like diagonal above it. It's like I don't know what you call the super diagonal above, like I actually say like super duper diagonal or something like that. Kind of funny. But yeah, essentially like hopefully like you want like big math, but like going like NC like n plus 1, like that should not be, you shouldn't get that essentially. Like I think the maximum gets like NCN. So something like that. Okay. And then of course like everywhere else you just put like zeros. Yeah. Okay. So then you have like direct sums of matrices. So like essentially like the A1 itself is a matrix. So it's not a number. It's a matrix. So like you put all these like kind of like oh, do they have examples? Yeah, okay. So like let's just do a random example. So if I have like J2 of like negative E, like a sum of like J of 3 of like just like 0. Actually no, that's kind of bad. Just like 5. The sum of that is like 2 plus 3, so like it should be a 5 by 5 matrix. So what I should have is negative E, negative E, 1, 0, and then this one here, it's like 5, 5, 5, 1, 1, 0. So notice how like this here is like corresponding to like this block, this is like corresponding to this block. And then obviously like every other entry of like freaking zeros. So okay, like I'm like safe like zeros, but something like that. So yeah. Once again, it's kind of like again like here, it's like this block corresponds to that. This entire block corresponds to this. Actually. So that's the whole purpose of like drawing form for now. Okay. Yeah, so you have like this other thing where like you can also compute like the powers and like these direct sums, like the Jordan blocks. So like the lemma is like you kind of like split it up kind of thing. So like this would equal to like n and then sum it with like the other one, but you also like n that. So like if you use the thing from above, then like this thing is just like J23n. Like this one here is like fine. That's chilling. Yeah. Okay, so generalized eigenvector. So like usual eigenvectors like like when this feels like 1, so that's kind of obvious. But when you have a generalized eigenvector, like when you power this thing, you can basically like get like sort of more eigenvectors like kind of out of that essentially. And if that makes it equal to 0, then like that belongs in like the set of like the generalized eigenspace. Okay, I'll say that later. But like for like some like random integer k, because if you power this, that may or may not like for like various questions I've seen, sometimes it goes to 0, and like sometimes like it just doesn't go to 0 at all. But like there's like some sort of pattern. Whereas like okay, like you basically see for the examples I see, but like that's like it's not necessarily like I guess like infinite because like it's could like terminate or may not. Like we don't know. Yeah, obviously like if k is 1, like that's the usual like that we know. Okay, so show that. Okay, so show like this is like a generalized eigenvector. So yeah, we have to like -5 off like the diagonals. So 4 -3 -3. Okay. Okay, so what can we do this? Okay, is there any like if this wasn't indeed a eigenvector of like C itself, not just like generalized, like I'm concluding like this thing has to be kernel 0. Just by looking, I don't think that's the case. Okay, so like whenever that happens, then you just have to like basically go up a level essentially. So I have to freaking do this matrix multiplication, like that thing multiply itself. So like at this point I'm just gonna cheat. So like I'm gonna use MATLAB. Yeah. Wow. At least it's not maple. Jesus. Alright. A is equal to 4, 7, negative 3, negative minus 2, minus 1, 5, negative 3. Okay, let's see what A squared gets. Yeah, okay, so this is good. So, minus 4 minus A, 4 is like it's going to be the double. So minus A, minus 16, 8. Okay, so like just to reiterate, like this is A minus 5I all squared. Yep. And then, yeah, let's try like if we can find the kernel of this. Because like this thing has one leading, it has R. Okay, then that kind of like, that kind of makes me think that the determinant of this, it might be, it actually might be 0. Oh no. Okay, back. Like, it makes me think the determinant of this actually is 0, but again, I have two sleeps. So, like for this one here, I have to find the kernel of that. The bottom is just like the multiple of the first. So let's just multiply this by, like divide by 4, like this, bunch of zeros here. And then to like, again, like find an eigen vector of that. Is this right? Wait. Minus 1, yeah, okay. So like through like your favorite method of like doing finding like the kernel of this at this point, like you'll see like, hey, like this actually does work. Like it's like minus 1 plus 4 minus 3, that's equal to 0. So like, yeah, it is an eigenvector. Or at least it's like a generalized eigenvector of this. I don't know if you need to prove like it is also an eigenvector of this because like as I'll say later, when you do this like powering of this kernel thing, you basically form or generate more eigenvectors, like more generalized eigenvectors that may or may not have been in like the original like say like eigen like space or whatever, like maybe like this one without the square. But yeah, like we basically had to square in order to like without the eigenvector. And also like if I like do like a cube, this thing will like you kind of like see the pattern here. Like it's kind of like multiply by 2 every time. So like you're not gonna get what is it? Like this thing will go to the zero matrix. Like you kind of like conclude that. So that's why it may not be like infinite essentially. Yeah. Okay. So like that. Yeah. So in general, basically, the eigenspace is like remember, it's like the space of like all the eigenvectors. But the generalized eigenspace is like basically just like all the vectors like that would satisfy like this equation like for like some k. Like you go for like each k values like oh like when k is equal to this, that's the usual eigenvector. K is 2, it's like the next one, like so on. Just keep powering that. Yeah, I never really saw this one here, but you kind of like represent it as like your union of like all your individual powers of like the kernel essentially. So yeah. Okay, so okay, Jordan matrix is it's essentially if it is obvious, like Jordan form, it's kind of like the extension to diagonalization when you don't have enough eigenvectors. And then that's basically when you resort to like Jordan matrices. So like diagonalization is like a subset of like Jordan matrices essentially. So like with that kind of in mind, we want to like sort of use the same ideas from like normal diagonalization, like kind of like this similarity matrices like form. Also like the Jordan form is also like a complete similarity invariant as well. So yeah. Okay. So I guess like you can prove like you with uniqueness that every like matrix has like some sort of unique join matrix. I guess you can like kind of like do that trick where it's like you're again like assuming like oh like let PJ be another form of like join matrix, but then you just like prove like oh PJ is actually equal to like J. I'm saying P is like pseudo. It's like maybe it's like another actual join matrix, but like you just like say it's like the same, so it's actually just unique instead. Yeah. Okay, so properties like computing join forms. So let's just be like a bunch of like long stuff here. But then what you'll find is that like the kernel of like your initial one, like it's not really interesting, has to be a subset of like the next like sort of power of like your kernel and like so on essentially. What this is saying, this is essentially like the way I kind of visualize this, which kind of helped me like visualize join chains that is. So uh what's the what's the oh yeah, GE. Yeah. Okay. Like maybe this like sorry. Let's say this like GE like one of like lambda, like whatever it is. When you essentially like power that matrix, then like that generalized eigenspace gets bigger. So maybe this like GE two lambda. So like when you like square the kernel. In that case, then what you do is like you basically farm more eigenvectors that may or may not have been in like this one here. So like this is if I grow like some B here, and that's like part of GE1, that's definitely going to be a part of GE2. But then if I get a vector from GE2, that may or may not be in GE1. So I'll go back to like saying this like when I'm talking about like the join chain. Yeah, maybe like one more time. Maybe like G3 or something. Yeah. So like every time I power it, then like yeah, I'm just like farming more like generalized eigenvectors. And then the thing here is like what's here? Oh, it's like the nullity, yeah. So like the nullity is like has to always increase. Like it can't be like just suddenly like decrease. Doesn't really make sense. But then this one here, that's saying that the gaps between the nullities of each successive power that has to not increase. So I think actually nah like I will cover later. But like the gaps between each like, successive nullity has to like it can't just like go to like okay like it can't just go like one like like this is fine because like the nullities are increasing, but I can't just like go to like 100 all of a sudden because the gap went to like 4 2, which is fine, but it went to like freaking like 93. So like that's like basically what it's saying here. Like it can't do that. So no. Yeah. Okay, so finally find the eigenvalues. So yeah, a bit seeps here, but like the this is the character's polynomial. How do I do the wait, so like I have to do minus this. Okay, so I guess 5 squared plus 5. Okay, good it is. Okay, so lambda minus 5 is a factor, and then lambda squared minus 8 lambda is 40, so it's plus 15. Okay, so it's gonna be like that and like minus 3. So the eigenvalues of this is like 5 and 3. So like know about like the multiplicity of 5 is 2. Oh, okay, well, yeah, no need to MATLAB this one. So if we just like minus off like the corresponding like just get like the corresponding like kernels essentially, basically get this. So yeah, so like once again, it's kind of like that pattern I was saying where notice how like this kind of like basically like won't go away essentially. So the nullity there will like still like stay as okay in this case like the nullity is like 2, so it will stay as 2. But it won't just like suddenly decrease over time. It's kind of like induction. So like like if it work for like the first 2 cases, then like surely it work for like forever essentially. And then for this one, yeah, so like unfortunately, like kind of like this one goes away, but then like this one here, like it kind of like remains persistent, I guess. So like this row will always be like there. So like the nullity in that one would be like 2 because you got like one leading column. Um, yeah, yeah, it's kind of like what I was saying there. It's like the nullity just like stops there, so it's just like as long as it's not decreasing, it's fine. Like if it's the same, it's fine. So like same again here. Um, but yeah, it's kind of like the point here is like it kind of like terminates like sort of this point. It just like won't go higher. Um, oh yeah, and also it's also equal to the eigenvalues algebraic multiplicity. So like when we got that like this one here. Oh no, wait, which one was it? Wait, which one had like the oh yeah, okay. So for like the lambda equals 5, because the algebra oh yeah, that was the algebraic AM was 2. No wait. Yeah, the aim was 2, but then the GM here, according to this one here, that must be equal to 1 because like we're looking at like 2 leading columns, like that's nullity of 1. Like if we then like power it enough times, then we actually will find like it will some at some point equal to like the geometric multiplicity, equal to the AM, that is. So the GM will actually equal to AM if we power it enough times. So it's kind of like the full process here. So let me do this. Okay, so like you basically like what this is saying here is like there's no way you can like freaking power it 3 times or something. But like essentially like maybe for computers or something, they only like computer up to like a specific power to the point where like the nullity is equal to like the AM. Because as you saw like on my session for Maple, MATLAB, I don't need like power so many times. It's like it's only gonna like stay it's only gonna like stay like some point and like it's gonna like stay there probably. So it's why they only do like specific powers of like this kind of thing, that is. Yeah. I kind of like said that already. Like the GM like has to be greater than 1. Like I don't know what it means. Like it feels like 0 and then it doesn't even make it's kind of pointless. Um yeah, okay, so like this is the bit of like join chains. So yeah, I'm gonna use that actually. I'm gonna copy here. I already forgot. Oh yeah, GE1, GE2, GE3. So my visualization of this is like, let's say like start up like some like vector here, um, in G3, that is. So it's like the cube of like the kernel sort of thing. Well, if we do this process here, then like how the join chain works is like it will basically send this vector into like the GE2 sort of space, that is. If you do it again, then you're gonna get sent like the GE1 case, which is like just the usual eigenvector. And then obviously when you multiply that again. So that is like when it's going to go to 0. So that's kind of like the visual way to like represent join chains, like kind of written here. So also like some other wait. Let me say no. I'm not gonna say it. Like a maximal Jordan chain. Maximal Jordan chain is if the Jordan chain itself is not like contained in another like bigger Jordan chain, that is. So, like if there's like another one here, that's not maximal. If the G4 was like the max, like I couldn't find any other Jordan chain, then like that I can like conclude it's a max. Um, so the importance of this is like whatever vectors I get out of my like my Jordan chain, that's gonna form my Jordan block or like my Jordan oh no, it's not gonna form okay, it's not gonna form the block, but it's gonna correspond to it essentially. You know how like when we had like P as like the eigenvectors of like your eigenvalues, like it's corresponding to like each of those eigenvalues. It's like kind of like the same thing here as well. Like corresponding to like its each respective eigenvalues, basically. Okay. Okay. So block diagrams or okay, I forgot that name. It was Young Tableau, Young Tableau. So yeah, it's like the same thing. Okay, so Young Tableau. So Young Tableau will basically like encode like all this information here. So it will code like the nullities of each one. So like the chains that or like the direct sums kind of, and like basically just like the structure, I guess, as well. So an example is like maybe it's like this. So John's eigenspace, all these nullities here. So the nullity is 5. Then we're gonna have like a Yeah, drew too many. I actually can't count. Take this. Yeah, so it's like a null tier 5 is like that. You go up like one more level. Yeah, we do it down. Like I think like previous is like they kind of like do it going up. Like yeah, I guess like Sean likes to go down this time. Here, so like the nullity is 8. So it's like the cumulative like kind of blocks at that point. So we need to add 3 here, so it's like this. And then add 3 more, I guess, because get up to 11. And then we get to 12 here. So like one more. So like what does this do here? So essentially like we can kind of like determine like the maximal Jordan. Firstly, we can determine the maximal Jordan chain I guess wait. Maximal Jordan chain like length. Which is basically the height of this, like the height of the blocks, which is also like the height of the eigenvalues. I didn't say this before, but where is it? Yeah, okay. Maybe like this example, like the height of an eigenvalue is it's kind of determined by it's like for something like oh that's not an example. Maybe like here, it's like the nullity of this suddenly changes when it's equal to when you power one more time. Then it will like kind of like lose that rank. It will lose a rank. So then at that point, or like anything that's fine. But then anything afterwards that like that, the nullity remains the same. So like the minimum k value to make that happen, essentially, for it to be this remain the same, that is the height of the eigenvalue. So again, it's kind of like we have like a little representation of like the height actually of like the blocks. So the maximal Jordan chain is determined by the height of the eigenvalue, like vice versa. But it's also determined like by this in like this Young tableau like format essentially. What else can we determine? We can determine the actual Jordan normal form, like the direct sums of each of them. And that would just be the sum of all of these columns. So like this thing, plus this thing, plus this thing, and like all these essentially. So, I mean, obviously there's like all the same eigenvalue, obviously. So that would be like this first one. That first one has has like 4 blocks. So it's gonna be like a block of 4, I guess, of like whatever eigenvalue you have. And you have a direct sum of like your next ones. So j of 3 lambda plus j of 3 again, plus, and then just a bunch of ones. So like 1 plus 1. Yeah, so like that. And notice how like this Young tableau it still keeps in line with the fact that like the gaps between each like blocks don't like they don't increase. Like this is it's like a 2, it's like a 0, that's fine. And then it's like a 2. So and like obviously like I'm not gonna see like something like this. Like that's definitely not gonna happen. So it still keeps in line with that. Otherwise like this case would be like impossible. Yeah. But I swear I just oh wait, no. Okay. Yeah. I'll explain why this one isn't possible. So again like do a bunch of blocks here. So 5 and then like 3 9, so like 1 and then 3 more, and that's the problem because up to this point it's like fine, but then you have like this like part that's like kind of jutting out. So remember that kind of like loops back to like I guess like if you want to just look at this like algebraically like the numbers, you can notice how like hey like the gap is like 3, this is 1, and I say like the gap here that can never increase, but then suddenly just go to like 3, so it just suddenly jumps in. It's like no, you can't have that. It has to always be not increasing. Like it can stay the same, but it just can't increase. That's it. So like obviously like the block diagram kind of shows like hey you can't really like it's kind of giant, so it doesn't really work. Yeah. Okay, 10 by 10. Then like to draw the Jordan forms essentially. So you know it's a 5 on the top again. 3, 4, 5. 3, so like that. 1 more, it's like that. The thing is that like it's like a 10 by 10. This is a 10 by 10. So like we have like one block to like distribute out. So like there's only like one place you can go essentially. Where's my oh, okay, I didn't even have it there. But like any other like I don't know what you're meant to do like place that block like here or something, but like it doesn't really, it won't like align with like what we just said, with like the 9. So that's like the only Jordan form here then. Yeah. Okay. Damn. So. All right. Calculate. So. It's the first one. Oh no, I can like minus them off first. So like 4, 73, minus 3, 1, 3, 5, 2. Okay, I don't know if this yeah, okay. What does this equal to? So 4 minus 14 plus 9. It's minus 1. Nah, it's minus 3. Okay. Minus 2 plus 6 plus 1. 2 minus 10 plus 9. 1. Okay, so this is clean. It's too fast. Let me check it. Oh, we already did it. Wait, I didn't realize that. Jeez, it's so far back. Yeah, okay, negative 1, 1. Okay, good. And then like I kind of like saw that as well. That thing was also equal to like this thing was 0, 0, 0. Yeah. So without using any matrix multiplications, write down all the eigenvalues. I mean, like, wasn't it? We already did this. So like, I believe there was like 5, 5, 5, like 3. Like even if you didn't do that, like you can do this like without like trying like look at the other ones, but essentially like what this is saying is remember like okay, I already forgot the theory name, but 5 is definitely an eigenvalue, because the generalized vector of this one, oh yeah, like that v here is a generalized eigenvector of it. So like that means like I was acting like some sort of double root because it's not going to make this 0, but it's going to make this 0. So we have like a double root going on. Like it was like to the power of 10, like we have like 10 5s here. So like we know these two would be like the eigenvalues. So again, you can just like, kind of like look at the other eigenvalues. But again, like if you didn't know that, just look at the trace. It's like the trace is like 13. So 13 minus 10 is like 3. So those would be like your eigenvalues. And then like once again, like this here, like okay, each of these. Oh wait, no, that's AM GM is both 1, so 3. But then for 5 here, so because the idea is that if we'd have another vector that's actually not necessarily okay, but the algebraic multiplicity of this, like surely that's 2. But then for the like the GM, that is, because we had to like kind of go up another power, because that's kind of implying that like, hey, we don't have enough eigenvectors in our original one here. Like there should have been 2, but like we didn't, and we had to like go up another level in order to get like make it like 2 at least 2 generalized eigenvectors. That is. So that's why like this one here, like the AM is still 2, but the GM would be 1 in that case. Yeah, what are the notes here? Divides at least 2, but it's not because 3 is the other one. Okay. Yeah. Okay, what's question 3 saying? It's like uninvertible matrix P and yeah. So now's the time we like Jordan chain this. So you don't have can I write? Doesn't need help. So again, P, like the analogy is like it's like your kind of your eigenvectors, but in this case, with like Jordan form, it's like your generalized eigenvectors. And the idea of like from diagonalization, where like I have to like write your eigenvectors in the same order as like your eigenvalues, that still is like the same idea. So maybe let's say we put wait, let's say J. So remember like the form of this should be like J of let's say 2 of like 5 and then direct sum with like j of 1 of 3, because that's the algebraic multiplicity. So what that should look like is like this, like 5, 1, and like 3. That's kind of on its own. So that'll be a Jordan form. Again, you can like rearrange it around like 0, 0, 3. Wait, no. Now you would say like 3 instead at the top, but like again, like order doesn't matter as long as you're consistent with it. So how do we form this like P matrix then? So this is the bit where you need to like get the Jordan chain part again. So it's kind of like again like that kind of analogy, like these kind of stuff here. You want to get a vector that's like kind of like the outside of like that's gonna start the chain essentially. And like once you like go further, once you get to the 0 vector, if your Jordan chain is like long enough, then that will form your like basis for like that part of like your P matrix. Like if you started here, right, and like you went you like did it twice essentially, and that's not gonna be enough. It's not really like a maximal length or something like that. So you basically gotta ensure that like your matrix, your vector like starts out like big enough essentially. So where is it? Like we kind of have that here already, because all we care about is having a Jordan chain of length 2. But we kind of just did that already, because we see that C of minus 5i of 1 negative. Okay, I'm just gonna write it here. 1 negative 2 negative 3. That's gonna go into, as we already saw, it's like negative 1 1 1. But then that's going to go to the 0 vector. So hey, we have a Jordan chain of length 2. So then when you're actually writing these vectors inside like the P matrix, then what you're going to do is like you kind of got to reverse it. So like the thing that's like at the end, like obviously not the 0 vector, put that as at the front. It's like negative 1 1 1, and then to like the very start, it's like 1 negative 2 negative 3. Okay, so that will be your part compared to like corresponding to like this part, that is. Obviously like the last one, that's like your usual eigenvector. I think we did find it somewhere. Okay, I'm not gonna scroll up. I'm just gonna scroll down this point. Okay, it was like 1 0 2, whatever that was. Okay, so that's that. And then yeah, like that's basically our P matrix. And then here is like the Jordan form. That is that. Yeah, okay, so it's the same. Cool. Okay, next one. So we're given this. We'll find the Jordan chain. Starting with 0 1 1. So again, it's like there's like hopefully like they'll get into some non-zero vector. So we just have got minus of 2 for each of these. So 4 minus 4 minus 7 2 2 2. Okay, like multiply that 0 0 1. I'm pretty certain it's the sum of these. So it's like minus 1, minus 3, minus 2. Okay. And then if we're going to chuck that inside, like another, like the C minus, no, like the A in this case, A minus 2i, minus 7, minus 4, you times that by minus 1, minus 3, minus 2. Okay, please work. That's 4 minus, okay, 0, 14 minus 12. Okay, 0. Okay, okay, 0, 0. Okay, good. Okay, I'm not worried about time because there might be people here. Yeah, so founding calculation about the geometric multiplicity. So because again, like there's like another like if all your generalized vectors are inside like of the vectors, so that it's like A minus lambda I, then the GM is the same as the AM. If you have like a generalized eigenvector for like some k that's greater than 1, you're gonna have problems. So, yeah. So this one here, like because like we not all the generalized eigenvectors are like the first like k is equal to 1, so then the GM has to equal to 1. Pretty certain about that, right? Yeah. Yes. Okay. And then finally, find Jordan form such that well that stuff. Okay, so again, like the J, that should equal to what are eigenvalues? Okay, so 2, 2, 1, 7. So the other eigenvalue should be 3. So 2, 2, 1. That's your block here, and then the other one's like a 3, so like that. so far, right? Yeah. Okay. Yeah. Cool. And then for your P again, this is like the vectors that are formed like the Jordan chain. So again, it's like go backwards kind of thing. So like it's like this is the thing that was the last thing before we got sent into the 0, 1. Oh yeah, so like right here. Minus 2, minus 1, minus 1, minus 3, minus 2, 0, 1, 1. And then the other, like the final one is going to be the eigenvector associated with that. So that one is, this one, 1, 4, 2. So we just use that right away. Yeah, like those are like your P and J, like matrices essentially. Yep. Okay. Okay, fine. V and, okay. This is kind of a pain. I don't know why this is here. Like, you basically just want to find specific linear combinations of your like what is it? Essentially, what you're doing is this: like -1, 0, 1, -3, -2, 1, 1, 4, 2. Like essentially like solving that. It's like the RFE thingy. So you find like specific linear combinations. That's a bit too serious. Okay. So like apparently sometimes you're not always going to be given like the starting vector to start your Jordan chain. So we may have to like be a bit smart here, like basically do some tricks here. So in here, like we say, oh, let's find some vector. So like it doesn't get sent to like the 0 vector, but like if you do it again, then you get sent to like the 0 vector. So let's try this. Like v1 is equal to, like instead of saying v2 right away, let's try to find like the kernel of this essentially. So you notice like that middle, sorry, the second column, that's like purely just all zeros. So if we just like say 0, 1, 0, 0, that's kind of like saying, hey, just take the second column. So obviously a minus 2i times like that vector here, that should equal to like 0. So like we found like vi like correctly. So we just need to find a v2 here essentially. So okay, we need like in 0, 0, 0, 0. Okay, like A, B, C, D this, because like we don't know what it is. But we do know that it has to equal to like V1 essentially. So like the first one, like 0, 0 is like who cares? Then A has to equal to 1. And then and then the next row, A minus D has to equal to 0. And then the last one, C plus 2D has to equal to 0. So B can be like almost anything, so that's fine. But then call it D has to equal to 1. So obviously C is equal to -2. So then V2 essentially can equal to 1. Like B can be anything, but if it goes like how do you get like maybe non-zero values? You actually like plus like this kind of thing. You're basically plussing like multiples of that. Because again, like that's in the that should be in the like the smaller case, like GE1 essentially, before you like square it again essentially. But like let's for now say it's 0. That is -2 and that's 1. So that is a vector that we can get to like basically start our Jordan chain. So like Jordan chain that we get like the E2 of like the basis thing, and then you do that again, then you get like 0. Yeah. Okay, so Hamilton theorem is kind of cool in the sense that like every matrix is like what do you call it? Characteristic polynomial. Every matrix would like satisfy its own like characteristic polynomial. So it's kind of interesting. So we're gonna use that here. So like let that be like some finite dimensional stuff. Suppose this. So use the Cayley-Hamilton theorem, like prove that V is an eigenvector of T. So okay, we know right off the bat that it's T. So T cubed minus 5T squared plus 10T minus 6. That has to equal to yeah, so just be careful because it has to be like I. So like this thing that has to go to 0. And like what can we do from here? Okay, so if this is in the image of that, there must be like some sort of there exists some U such that t squared u minus 4t u plus 6i u is equal to v. So we're going to try to use that along with this here. Try to see what we can do from here. We can move this to the other side. So like t cubed is equal to 5t squared minus 10t plus 6i. Okay. And then, oh wait. Yeah, okay, that's fine. Ooh, okay. So for this equation here, like it's a bit misleading because like this is still a bunch of matrices, but like this entire thing, like what is like the left or the right? That should be a vector. But for this though, what if we can do like t both sides. So like we can do like I'm really running out of space. Like t cubed minus 4t squared u plus 6. Okay, like when you t I, then the I will just go away. So you just have t. That t of v essentially. So it's like okay, great. Like what do we do with this? Okay, how do we? I know that the t cubed, like okay, tv is equal to. So saying t cubed, I can replace it with this like a gigantic mass. So 5t squared minus 10t plus 6i, and like all the stuff. Okay, u minus 4t squared u plus 6t t of u. All right, so that's equal to t squared u minus 10t u. How do I sort this out? 6i u thing. Okay, because like I'm like really close to this. Like that's basically what we're trying to prove there. How does it not go away? Let's just write it out. Okay, 6i. Okay, it's like when we have that, then like it's like 6u anyway. Then okay, and then wait, it's minus 10 plus 6. Oh wait, I can't wait. I don't wait. This thing will cancel. But then this thing is like 6t of u minus 10t of u. That's equal to minus 4t of u. So, like I thought like this thing would remain unchanged, but like it's not. Okay. So it's like 6 minus 10, so it's minus 4t of u. But then this thing will like remain unchanged. That's fine. Okay, so you can like say, thinking like, yeah, like that's fine. But notice that this thing here, that's nothing else but just v. So what we just found, t of v is then equal to v. So then by that kind of conclusion, like oh yeah, v has to be an eigenvector of t, and then obviously like the eigenvalue is like 1, like 1 times v. So yeah, okay, so stop. Okay, matrices, exponentials. What do you have left? Okay, we have like 9 more pages. Okay, that's good. Okay, for square matrix, so you remember like from like Taylor series of like e to the x or whatever, it's like the sum of like the factorials, like the power stuff. So it will be kind of nice, like maybe like generalize this to vectors and like see, matrices, and then see if that's the case. So if the matrices commute, that is like oh yeah, A, B, and B, A, then you can basically like split up the matrices or like combine them. Like it's kind of similar to like the real numbers like scalars. Then the inverse of exponential of A is going to be like the exponential of like the negative. So again, kind of like aligns with our, I guess, you call it like scalar field like understanding. This one though is kind of a bit weird because like if you take the derivative of a matrix inside of a exponential, but like that's like measured with respect to time, then you kind of get out the A part, which is like really a bit weird. But like again, if you punch in like the math, like it does work out anyway. Okay, I'm just like again. What? Okay, like under 2 hours. So you might find like, hey, if you're gonna like calculate the power of like some sort of actually wait, let me say this. Okay, so like calculating matrix exponential, like it may be like a bit beefy for like computers to calculate, but if we use specific parts of diagonalization or even like this like Jordan form, then that makes it a bit easier for like I guess like calculus or even us to like calculate. So if you have the if you represent like diagonalized like that sort of thing, then the exponential is like the same like sort of diagonal like matrix like the diagonal eigenvectors kind of, but then you exponentiate the diagonal. And what is that then? The exponential of a diagonal matrix is like really easy. Like if you have like 1, 2, just like that, then the exponential of that is just equal to like you just basically exponentiate like each one of those like this. So it's like kind of easy. And then if you have the direct sum of a bunch of matrices, then the exponential is also like the direct sum of each of the exponentials as well. So it's also kind of neat to keep. Finally, if you have the exponential of like maybe it's like some variable t followed by your your Jordan form, that is, it's equal to like you would put the exponential inside here, like we just took it out for convenience. So it's all equal to like 1 on the diagonal, but then on the super diagonal, it's like it's basically it's like the terms of like the exponential like this kind of thing. So it's like 1's there and like t, but then you kind of like do the factorial thing, and then you keep doing it to like the very like end, I guess. Assuming it's like I'm assuming it's a k by k. So like obviously you wouldn't reach like t to the k anyway. Yeah. So those are the properties of good. So yeah, like here's like an example here. You take e to the 2 out there, but like yeah, all this stuff is like the kind of like the Taylor series of like exponential. So you're all fine. Yeah. Okay, so a quick example, blah blah blah. We want yeah. Okay, so like basically it's asking us like to calculate this. So I already like did the work for this. So you recall that like e to the jt. Oh wait, yeah, e to the jt. That's essentially equal to our eigenvalue times by t. So I kind of already forgot the eigen. What's the eigenvalue associated with that? Oh, okay, no. So this is the part we have to like do like the direct sum part. So it's only part of the matrix that you want like to like have this kind of like specific form. Like other parts of it, which is like the eigenvalues like is the eigenvalue like that's not part of the Jordan form. Like use plus on like each of that just usually kind of thing. So like essentially like the exponential of this part is because remember like the direct sum, we do these individually. So that's equal to e to the 5t. And then we have like 1, 1, and then like t. So that's like for like the first part of the Jordan part. The second one though, e to the 3t, like the eigenvalue is just like one value. So like it's just e to 3t. So that's like one like entry. So we're like kind of like combining these like the direct sum of like those two. Then instead of like the Jordan blocks, like get each block and then just like direct sum them. So it's equal to e to the 5t, e to the 5t, and it's like te 5t, like that. But then this thing down here is like e to the 3t. Obviously everything goes up like 0. So that is our like the exponential of the Jordan block. And then the p's just like leave those alone. Like no need to worry about them. Yeah, like it's like yeah. Okay. Oh yeah, so like yeah, against like the parts like you can do these like individually, direct sums and all that. Okay. Column method. So okay, if you have like your random Jordan chain, then essentially like the exponential times by like some vector is equal to, and then like it's just like your like whatever eigenvalue that you're evaluating at, followed by like basically like the vectors following your Jordan chain essentially. So this would be like the start of like your Jordan vector, and then you just keep doing it's like this should be like the last vector before you get like the zero vector essentially. So that's the column method. So yeah, here we can do like solve a homogeneous T. I'm not gonna do inhomogeneous because it's not in the test. Yeah, so like the temp time like uses matrix here already. But here we have like the matrix there, and then that's how starting like vectors start the join chain. And then we just need to solve the initial value problem. So like again, like remember like from 1b, it's kind of like dx and dt is equal to like 9x plus 7y minus like 3z. Like obviously it's the other three the other two that is. And then here we actually have like an initial condition, given that it's actually like y of 0 is equal to v. So again here, it actually might be reasonable to guess like kind of like use this like Jordan chain like this one right here kind of. Okay, I just gotta check. Okay. Right. Okay. So it's gonna be equal to e. Which eigenvalue are you using? Oh, we're using like 5. Okay, so again, like e to the ta of our like initial like starting like fact like that's the initial state. It just so happens that it is the starting eigenvalue. In fact, it's the starting eigenvector is also equal to like it's also like the initial vector as well. But so now we're gonna times out like this because it's like the exponential t of a that will encode all the information we need to like actually solve the DE. But the reason we're timesing by the V1 is because we're doing that to like get the initial state because like this is like the general solution, but then this will essentially force the like the specific solution. So that's kind of like that. Yeah, so it's the exponential of this, and notice how like we don't even need to like do any like diagonalization, like the Jordan form, like none of that. Like all we care about is like if we have like the Jordan form, that's actually all we need. Because again, it's like that's like the whole purpose of like the column method. As long as you have like this thing here on the outside and like all your vectors that on the Jordan chain, and that's enough essentially. So please load. Okay. Like essentially that is equal to the eigenvalue associated with our starting join chain is like 5. So like e to the 5t. Put it right here. Wait, e to the 5t. And then just your like the starting wait, which one is it? The one that started it. Okay, so the one that started here was like 1 minus 2 minus 3 and then plus yeah, okay. Plus and then like t of like our next one, so like the -1, 1. Yeah. Like if this Jordan chain was longer, then we'd have to do plus like t squared. So it's like literally just the t squared on 2 that is sorry. Like the factor is like the same terms as like the exponential kind of thing. Yeah, so it's like it kind of looks like a pseudo like Taylor series for like EDX sort of thing. Yeah. And then this is equal to e to the 5t. So it's like 1 minus t, minus 2 plus t, minus 3 plus t. Yeah, okay. So that is essentially how we like solve this I guess like these differential equations with like the column method. So yeah, pretty cool. Like if we're only given like the join chains, but like we don't need to like do any join forms or that. Okay, yeah, that's it. Jesus Christ. Yeah, okay. So like yeah, I don't really have like much else to say. Yeah, this is like yes, up to okay, easy. Yeah, like good luck with exams, everyone. Yeah, all right, cool.